Recall the Lorentz transformation for locating an event in the K reference frame. We had x equals to gamma into x prime plus vt prime, y equals to y prime, z equals to z prime, t equals to gamma into t prime plus v on c squared x prime. Now gamma is equals to 1 divided by square root of 1 minus beta, where beta is capital V on c. Knowing that coordinates of an event is given by x, y, z, ct in the K reference frame and x prime, y prime, z prime, ct prime in the K prime reference frame, for convenience, ct equals to x0, x equals to x1, y equals to x2, z equals to x3, and ct prime equals to x prime 0, x prime equals to x prime 1, y prime equals to x prime 2, and z prime equals to z prime 3. Now, if we make t the subject here, we have t equals to x0 on c, and if we make t prime the subject here, we have t prime equals to x prime on c. The rest remain unchanged. Now, in this equation, we're going to have t substituted by t equals to x0 on c, and t prime replaced by t prime equals to x prime not on c. Substitutions for x, y, z, t, x prime, y prime, z prime, and t prime in the system of equations above gives x1 equals to gamma into x prime 1 plus v x prime not on c. So I've actually substituted for x, x prime, and t prime what we have determined here. X2 equals to x prime 2, that's exactly what we have over here. That's x equals to x1, and we'll have x2 as y, which will substitute there, and x prime 2 as y prime, which we'll have there, and x3 equals to x prime 3, that's z prime is x prime 3, and z prime is, and z itself is x3. x0 on c equals to gamma into x prime 0 on c plus v on c squared x prime 1. Now simplify, cancel out common terms. So here are the denominators, we have c squared, so we have some common c's there which can cancel out, and that gives us, we have x1 which is that, x2 this, x3 that, x0 now becomes gamma into x prime 0 plus v on c x prime 1. We write the equation starting with x0 to x3, so we're going to rearrange this. So we have x0 bring up here, so we have x0 in ascending order of superscripts, so that we have x0 equals to gamma into x prime 0 plus v on c x prime 1, x1 equals to gamma into x prime 1 plus v on c x prime 0, x2 equals to x prime 2, x3 equals to x prime 3. So that implies that x0 equals to gamma into x prime plus beta x prime 1, x1 equals to gamma into x prime 1 plus beta x prime 0. The rest remain unchanged. So actually what has happened is that v on c has been replaced by beta. So here we have gamma equals to 1 divided by square root of 1 minus beta, and beta equals to capital V on. Expand the brackets and write the variables in order of ascending superscripts. So actually the right hand sides can be arranged in such a way that start with x, the not the zeroth components, and write in ascending powers. So I have gamma x prime 0 plus gamma beta x prime 1, gamma beta x prime 0 here plus gamma x prime 1, and then here you just have x prime 2, x prime 3. So each expression on the right hand side of each of the equations can be made to have 4 terms by adding the required number of zeros to each of the expressions, which leaves the expressions unchanged. That is, we can just add 2 zeros to the first equation there, that's plus 0 here, because we have x0 x prime 1, so we're adding that to make up like 2 and 3 here. So we have these two components, we'll add the 2 zeros there to make it 4, 0 plus 0. Here we have 0 plus 0 plus x prime 2, so this 0 here is just like in the place of 0, this 0 here is in the place of 1, this x prime 2 is there, plus 0 here which is in the place of 3. Then here we have 0 plus 0 plus 0 plus x prime 3, so this is in the place of 0, 1, 2. Now the zeros can be replaced with variables multiplied by zeros, meaning that there we have 0 times x prime 2. So as I said, 0 there is in the place of 2, that's why we have 0 times x prime 2, and here we have 0 times x prime 3. That goes the same for the next equation, so we have 0 times x prime 2 plus x 0 times x prime 3. Then for the third we have 0, this 0 multiplies x prime 0, it is in position 0, so we have the 0 times x prime 0, and the next 0 is in position 1, so we have 0 times x prime 1, and we have x prime 2 there, and plus 0 times x prime 3. Then in the last equation we have 0 times x prime 0, that's 0 in position 0, and we have 0 times x prime 1 there for the 0 at position 2, 1, and 0 times x prime 2 for this one at position 2. The four equations can be written as a sum of terms. So we can clearly see that this x prime 0, x prime 1, x prime 2, x prime 3 can be some variable x prime k, and then the coefficients can be alpha ik, such that we have xi equals to the sum from k equals 0 to 3 of alpha ik x prime k. So this x prime k here are the variables x prime naught, x prime 1, x prime 2, and x prime 3, and alpha ik represents the various coefficients of these variables. The above system of equations can be written in matrix form since the variables can be factored out as a common matrix. So actually, the left hand side gives us this matrix here, which is x0, x1, x2, x3, and the right hand side gives us a certain transformation matrix, this here, and the variables, this other matrix here, which is like a vector. This relationship can be seen as a linear transformation from x prime to x, so you can actually see a matrix multiplying this vector and transforming it to this other vector. Now, that transformation matrix is given by alpha ik equals to this. The Lorentz transformation x prime to x in the Einstein's convention can simply be written as x prime equals to alpha ik x prime k. So actually this alpha ik is that transformation matrix, xi are the components in the k reference, and x prime k are the components in the k prime reference frame. So we already know that xi is given by this, alpha ik is this, x prime k is also this. To transform from x to x prime, the following relation can be used. So actually, to do the inverse transformation, that's from the prime to the unprimed, we have to use x prime I equals to alpha inverse. So the inverse of this, because like you are trying to make this a subject, you multiply both sides by the inverse, and that's why you have this inverse times now the unprimed. So now, how are we going to get this matrix? That's where our point of interest is going to be. So know obviously that where x prime I equals to this, xk equals to this. So you can see the only difference is that this is in the k prime reference frames, this is in the k reference frame. Take note that only the notations have changed. Each matrix is the same. That is, primed remains prime and unprimed remains unprimed. So no matter if I put I or k, we have to take note that it's transforming from the unprimed to the primed. Clearly, alpha inverse ik is the inverse matrix of alpha ik, which we are about to find. It will be very fast to find this inverse matrix using Gaussian. Take note that in this section of physics, the first row is R0, the second is R1, the third is R2, and the fourth is R3. With this in mind, the inverse can be determined. Firstly, an augmented matrix is written as shown below. So we have the Lorentz transformation matrix augmented with a unit matrix of dimension 4. So firstly, we divide the first row, that's R0, by gamma. So here we divide by gamma to make this component 1 unity. So we'll divide this by gamma, by gamma, by gamma, by gamma, all of the first row by gamma, and we divide all of the second row by gamma, that's R1, this row. We'll divide all that by gamma. So that yields to this. So you see here we no longer have gamma, but here we have 1 on gamma, then zeros there, then you have 1 on gamma, zeros there. These other terms have little or no effect. Now let's see what else we can do. We have to transform this term to 0. So what can we do? We take R0 minus beta R1, meaning that you multiply this term by beta and do a subtraction. That's this row minus this row, then replace it in row 1. So when we do that, we have 1 minus beta squared. That's to make the second component 0. So we have 1 minus beta squared, 0, 0, 0. Then this guy remains. That's the other component remain. Now on the other side, we have 1 on gamma minus beta on gamma, because normally you have to multiply this term by beta, then take 0 minus this. So this is why we have minus beta on gamma. Now we have 1 minus beta squared there, so we need to make it unity now. So we have R0 replaced by R0 divided by 1 minus beta squared. So in all of the first row there, we are going to divide by 1 minus beta squared, which gives us this, meaning that you have 1 there, then you have 1 on gamma into this because we have divided by 1 minus beta squared, and you have minus beta into divided by gamma into 1 minus beta squared. Now let's concentrate on the second row. On the second row, we can try to eliminate this guy by this term. So we need to make this term to be 0 because it's already unity. Now we can make use of the first row. If we multiply the first row and take the second row minus that result, that's r1 minus beta r0, this is what we have. So we can actually see that the matrix on the left hand side is actually the unit matrix, while that on the right hand side is now the inverse matrix, which we have to simplify. So you can actually see that the second row here, after doing the multiplication and subtraction, is given by this and this. Now we need to simplify all these terms and see what they give. Now recall that gamma is equal to 1 divided by the square root of 1 minus beta squared. So gamma squared will equal to 1 divided by the square root of 1 minus beta squared. So you can just say that this denominator here is 1 divided by 1 minus this denominator. So this denominator will be eliminated by replacing. So when that is done, wherever we had that denominator, we now have gamma squared on gamma, like for this first term, minus gamma squared on beta on gamma. Also, this term here was having 1 minus beta squared at the denominator, so obviously we have gamma squared now brought in to replace that. Now when you do that, you see that some terms cancel out. So like this cancels with 1 gamma there, this cancels 1 gamma, this cancels 1 gamma there. Now let's concentrate in these brackets. We'll take the LCMs and try to make 1 and this fraction have the common denominator, and that gives us this. So you can actually see that some terms still cancel out, as minus beta squared cancels out with beta squared. So at the end, we now have gamma here minus gamma beta 1 on gamma, and this term here. So actually we had earlier seen that this term is gamma squared, and when we do that replacement, we have gamma squared on gamma. So obviously 1 gamma cancels this gamma down here, and we result now to the inverse as gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 0 1 0 0 0 0 1. So that gives us the inverse of the Lorentz transformation matrix. Now let's analyze that matrix again. If we try to rewrite the matrix in such a way that we affix the negative sign to beta, that's like how, say, this minus sign is carried by beta, so we have gamma into minus beta and gamma into minus beta here. And recall again that our Lorentz matrix itself was gamma beta 0 0 gamma beta gamma 0 0 0 0 1 0 0 0 0 1. Now we'll see that if we replace in this matrix minus beta, it quickly gives us the inverse. So you can clearly see that these two matrices are like the same, except for the fact that wherever we have beta in the, we have replaced by minus beta. So a simple transformation can be given from the inverse of the matrix to the Lorentz matrix itself. So you can see that the inverse is given by replacing minus beta in the Lorentz matrix. So everywhere we have beta, we replace by minus beta, and that will quickly give us the inverse matrix. So that's the simplest and fastest method to use to find the inverse where necessary. Thank you.